Hello everyone and welcome to Danesh Academy YouTube channel. Today we're gonna explore the topic of information theory and examine the entropy of information sources. The topics we will cover in this video are information measurement, entropy, mutual information, data processing inequality, and in the final, differential entropy. The source is typically modeled as a random process which can be discrete or continuous. Our discrete source includes a finite and countable alphabet and will be represented by a probability mass function. Conversely, our continuous source consists of an uncountable alphabet and will be represented by a probability density function. Consider the example of flipping a coin where the sample space consists of heads and tails forming a countable and finite sample space. The probability of getting either heads or tails is equal to 1/2. Now, let's consider a continuous information source. Imagine a real number between 1 and 2. As you can see, there are infinitely many numbers between 1 and 2 forming an infinite sample space. Now let's take a look at this question. How much information an event gives us after occurrence? An event with lower probability carries more information and also have greater uncertainty. Conversely, an event with higher probability carries less information and entails less uncertainty. Now let's analyze two news reports. Weather forecasters announced that it will snow in Egypt tomorrow. As you know, Egypt's weather is typically sunny and clear, so this announcement indicates a lower probability event, those containing more information. Now, let's examine the second news report stating that the weather in Egypt tomorrow will be sunny. This news is quite logical and common given in Egypt's typically sunny weather, indicating a higher probability event and containing less information. So, we observe that the lower the probability of an event, the more information it carries, and conversely, the higher the probability of an event, the less information it contains. Here we define the self-information, which measures the amount of information associated with a specific outcome of a random variable. It quantifies how surprising an event is given its probability of occurrence. It means the less likely an event, the higher its self-information. And finally, this can be calculated using the following formula. As previously mentioned, in tossing a fair coin, our sample space is denoted by H and T, representing heads and tails respectively, with each having a probability of 0.5. Additionally, the information value of each event can be calculated using the provided equation, with the information value of each event being equal to 1 bit. In fact, each of these events can represent H and T with 1 bit. In the third example, consider a source that only has two symbols 0 and 1, with the probability of symbol 1 being 1/4 and the probability of symbol 0 being 3/4. The information of each symbols can be calculated using the provided equation as follows. Now we have two cases. First, we will extend the concept of self-information to the case of dependent events. The joint self-information and probability of both events occurring together are defined as follows. When we have two events, xi and xj, that are dependent, the self-information of joint event is different from the sum of the self-information of each event. This is because of occurrence of one event affects the probability of the other. Next, we will explore the extension of self-information to the case of independent events. The joint probability and self-information for both events occurring together are defined as follows. When two events, xi and xj, are independent, the occurrence of one does not affect the probability of the other. This simplifies the calculation of self-information for the joint event. Now we'll go through an example to illustrate how to calculate the average self-information, also known as entropy, for a pair of events xi and yj. Consider the following probabilities for the pair of events. To find the average self-information, or the entropy, we take the sum of the products of each probability and its corresponding self-information as follows. Examining the tree diagram of example 4. The first question is whether 0 and 0 have occurred. If the answer is yes, the event 0 and 0 occurs with a probability of 9/16, and if the answer is no, we move on to the event 1 and 0. Now, if the answer is yes, the event occurs with a probability of 3/7, and if the answer is no, we move on to the event 0 and 1. If the answer is positive, the event 0 and 1 occurs with a probability of 3/4, otherwise, the last event, which is the event 1 and 1, occurs. Finally, the average number of questions required to reach the answer is calculated as follows. In this section, we will explore the concept of entropy, a fundamental measure in information theory that quantifies the uncertainty or unpredictability in set of outcomes. First, let's observe the image of 4 cats. This scenario represents high information with low uncertainty. Since all 4 outcomes are the same, there is little to no uncertainty about what we will observe. Consequently, the entropy is low because the information is highly predictable. Next, consider an image with 3 cats and 1 dog. This scenario has medium information content and medium entropy. While there is some variety with the introduction of a dog, the outcome is not entirely predictable but still not highly uncertain. The presence of mostly cats and 1 dog adds some degree of unpredictability, leading to a moderate level of entropy. Finally, look at the scenario with 2 cats and 2 dogs. Here we have low information content and high entropy. The equal distribution of cats and dogs means that each outcome is equally likely, maximizing the uncertainty. This scenario has the highest entropy because the unpredictability is at its peak with a uniform distribution, reflecting the maximum level of disorder in the system. To better understand entropy, let's consider a simple example. First, observe the first line where we have 4 cats. Here the probability of each cat being chosen is 0.25 and the sum of all probabilities is 1. This makes it straightforward to guess that my pet is a cat because there is no other types of pets present. The certainty is high and thus the entropy is low. In the second line, we have 3 cats and 1 dog. The probability for each animal is still 0.25. However, the total probability for cats is now 0.75, while for the dog, it's 0.25. Since the probability of choosing a cat is higher than choosing a dog, our best guess would still be that my pet is a cat. Here, there is some uncertainty introduced by the presence of the dog, leading to a moderate level of entropy. Finally, look at the last line, where we see 2 cats and 2 dogs. The probability for both cats and dogs is now equal, each being 0.5. In this scenario, we can't confidently guess whether my pet is a cat or a dog because the probabilities are the same. This situation indicates the highest level of uncertainty or entropy since there is no dominant outcome and both possibilities are equally likely. This slide examines the probability of entropy for each example. In the first case, the probability of my pet being a cat is 1. The probability of winning is 1 and the entropy is calculated as 0, indicating no uncertainty. It means that we are 100% sure the pet is a cat. In the second case, the probability of my pet being a cat is 0.75 and a dog is 0.25. The calculated entropy is higher than the first case, reflecting increased uncertainty. In the third case, the probabilities for cats and dogs are both 0.5. The calculated entropy is 2, means the highest, indicating maximum uncertainty when probabilities are equal. Now, let's explore the entropy of English letters. In the first example, we have 8 A's. This scenario has low entropy, making it easy to guess a letter. In the second example, there are 4 A's, 2 B's, 1 C, and 1 D. This situation presents medium entropy and moderate difficulty in guessing a letter. In the third example, we have 2 A's, 2 B's, 2 C's, and 2 D's. Since the probability of each letter is equal, this example has high entropy and makes guessing a letter very difficult. Here we will examine the entropy of different sets of letters as shown in the table and understand how it varies based on distribution of probabilities. First, let's look at the first set, which consists of 8 A's. Since all the letters are the same, the probability of choosing an A is 1 and the probabilities of any other letter are 0. In this case, there is no uncertainty in our choice and thus the entropy is 0. Next, consider the second set, which contains 4 A's, 2 B's, 1 C, and 1 D. Here, the probabilities and the entropy for this set is as follows. This results in an entropy value of 3.75. The presence of different letters introduces some uncertainty, increasing the entropy compared to the first set. Finally, let's look at the third set, which contains 2 A's, 2 B's, 2 C's, and 2 D's. The probabilities for each letter are equal, and the entropy for this set is calculated as follows. This calculation results in the highest entropy value of 4, reflecting the maximum uncertainty due to the equal likelihood of each letter. Entropy is a fundamental concept in information theory that measures the average self-information of sample space X. It quantifies the uncertainty or unpredictability associated with a set of outcomes. The entropy of a discrete random variable X with possible values x1 through to xn and a corresponding probability mass function is given by the following equation. This equation represents the sum of the products of the probability of each outcome and the base 2 logarithm of the probability multiplied by -1. Consider the source X, where the probability of x equal to 0 is 1/2, the probability of x equal to 1 is 1/4, and the probabilities of x equal to 2 and x equal to 3 are each 1/8. The entropy of the source X can be calculated as follows. Let's examine the tree diagram for example 6. First, we ask if x equals to 0 occurs. If the answer was yes, x equals to 0 happens with a probability of 1/2. Else, we move to the next question. Now we ask if x equals to 1 occurs. If yes, x equals to 1 happens with a probability of 1/2. Otherwise, we move to the next question and ask if x equals to 2 occurs. If the answer was yes, x equals to 2 happens with a probability of 1/2. And if not, x equals to 3 happens with a probability of 1/2. We can determine the probability of each symbol using this formula, and each symbol can be encoded using Huffman coding. A comprehensive video about Huffman coding is in our channel, and you can watch this and gain complete knowledge about Huffman coding. Now we calculate the average number of questions by multiplying the number of questions asked for each symbol by the probability of each symbol's occurrence. Summing these results give us the entropy or the average number of questions. In example 7, the sample space X has two symbols 0 and 1. The probability of symbol 0 is P and the probability of symbol 1 is 1 minus P. The entropy of this example is given by HP, a concave function. As shown in the graph, the continuous entropy is 0 at probabilities 0 and 1, and HP reaches its maximum at probability of 1/2. As previously mentioned, when the probability is 1/2, we have the highest entropy and uncertainty. The entropy for a uniform distribution is at its maximum. On this slide, we present Theorem 1, which addresses the concept of maximum entropy. Let's assume a sample space X. According to the theorem, the entropy of the sample space satisfies the following inequality, where n is the number of possible outcomes in the sample space. Equality holds if and only if the probabilities of all outcomes are equal. In this case, every outcome is equally likely. When the probabilities are equal, the entropy reaches its maximum value. This indicates that the uncertainty is at its highest value when all outcomes are equally likely, providing the maximum amount of information. Now let's move on to the proof of Theorem 1, demonstrating the bounds of entropy. First, we rewrite the entropy difference by expressing the difference between the entropy and base 2 logarithm n. Second, we use logarithmic properties and we apply this property to rewrite the terms. After that, we apply this inequality to bound the expression. Next, we simplify the resulting expression to show that it is less than or equal to 0. And finally, we conclude that the entropy is always less than or equal to base 2 logarithm n. Now, let's examine the concept of joint entropy. Joint entropy, denoted as Hx and y, represents the entropy of pair of discrete random variables x and y. It measures the amount of uncertainty or information contained in both variables together. The joint entropy means Hx and y is defined as follows. In other words, joint entropy accounts for the uncertainty in both random variables simultaneously, considering the combined outcomes of x and y. Here we explore the concept of conditional entropy. It represents the amount of uncertainty remaining about the random variable y, given that the value of another random variable x is known. It quantifies the amount of information needed to describe y when x is already known. The conditional entropy is defined as follows, and this can be written using the joint entropy means Hx and y, and the marginal entropy means Hx. This equation shows that the conditional entropy is the difference between the joint entropy and the marginal entropy. In other words, conditional entropy measures the remaining uncertainty about y after accounting for the information provided by x. Now here we explore the chain rule for entropy. As stated in Theorem 2, we have this equation. This theorem tells us that the joint entropy of two random variables x and y can be decomposed into the sum of the marginal entropy and the conditional entropy. To understand why this is true, we start with the joint probability. By taking the logarithm, we have this equation. Now, the joint entropy is defined as the expected value of the negative logarithm of the joint probability. By substituting the logarithmic identity, we get this equation, and then this separates into two parts. Thus, the chain rule for entropy is proven. It allows us to decompose the total uncertainty into the uncertainty of one variable plus the additional uncertainty of second variable given the first. Joint entropy is reversible, and this theorem can be proven using this relationship and the second theorem. Additionally, if joint entropy is reversible, we have the following relationship. By switching the sides of the equality, we arrive at the mutual information formula. Let's better understand joint entropy and conditional entropy with this example. Suppose two symbols x and y have values 0, 1, and 2, and the sum of x and y must be 0, 1, or 2. The probability of each symbol is equal to 1/6. we calculate the entropy of sample space X, the entropy of sample space Y, the joint entropy, and the conditional entropy of these two sample space. Joint entropy is easily calculated using the following formula. Now, let's delve into calculating the entropy of X and Y. We will start by examining the probabilities associated with each possible state of X and Y. For each state, we will calculate the conditional probabilities which tell us the likelihood of Y given a specific value of X. By analyzing these probabilities and their variations across different states, we can determine the entropy of X and Y. Entropy measures the uncertainty or information associated with each random variable independently. Next, we focus on conditional entropy, starting with the scenario where X equals to 0. Using the conditional entropy formula, we calculate the uncertainty of Y given that X equals to 0. Similarly, we compute conditional entropy for X equals to 1 and X equals to 2, incorporating these values into the conditional entropy formula to capture their respective uncertainties. Moving forward, we calculate the entropy of sample space X and Y, assessing their individual information content. Employing the chain rule for entropy, we combine these entropy values to achieve the joint entropy, revealing the total uncertainty when considering both X and Y together. Now let's take a look at Theorem 3, which states that the conditional entropy of two random variables X and Y given Z can be decompressed as follows. This theorem essentially tells us how to break down the conditional entropy of a pair of variables given another variable into more manageable components. To understand this, let's delve into the proof. We begin with the joint probability distribution of X, Y, and Z. This can be further broken down as follows. By recognizing this, we substitute to get this equation. Next, we take the logarithm of both sides. This shows that the logarithm of the joint conditional probability can be separated into the sum of the logarithms of the conditional probabilities. Finally, the rest of the proof follows similarly to Theorem 2, demonstrating how these components sum up to give us the total conditional entropy. In this slide, we present Theorem 4, which states that side information Y helps decrease the uncertainty about X, except when X and Y are independent. More precisely, conditioning never increases the entropy, which can be mathematically expressed as follows. This inequality holds with equality if and only if X and Y are independent. To understand this concept better, let's move on to the proof. For the proof, we use this well-known inequality and also utilize this fact. These principles help us show how conditioning on additional information Y does not increase the uncertainty about X, and in most cases, it decreases the uncertainty. Now, let's delve deeper into the proof of Theorem 4. We'll start by expressing the difference between the conditional entropy and the entropy. This can be further simplified by recognizing the definitions and properties of joint and conditional probabilities. Next, we rearrange the terms and factor in the sums. This equation reflects the relationship between joint and conditional probabilities and their logarithms. Finally, we substitute the definition of conditional probability. This final expression clearly demonstrates that the difference between the conditional entropy and the entropy is based on relationship between the joint distribution and the product of marginal distributions. Continuing with the proof of Theorem 4, we left off at this expression. To simplify this, we can use this inequality, and with applying this inequality, we can get this equation. This simplifies further to this, and recognizing that the first term is the sum of the product of the marginal probabilities and the second term is the sum of the joint probabilities, we have this equation. Since the summation of marginal probabilities equals 1 for both X and Y, the expression simplifies to this. This concludes the proof, showing that the difference between the conditional entropy and the entropy is non-negative, and only equals 0 when x and y are independent. Continuing with the final part of the proof of Theorem 4, we now focus on the conclusion. We have established this. With equality if and only if ln z is equal to z minus 1, which happens for this. Therefore, this implies this for the case when x is independent of y. This relationship confirms that the entropy of x given y is equal to the entropy of x itself only when there is no dependency between x and y. The graph on the right visualizes this concept, showing the inequality and highlights where the equality holds. In this slide, we introduce lemma 5, which focuses on joint entropy for two random variables x and y. Lemma 5 states that for two random variables x and y, we have this, with equality holding if and only if x and y are independent. To understand why this is the case, let's look at the proof. By the definition of joint entropy and using the result from Theorem 4, we have this equation. Since conditioning reduces entropy, we know this. Therefore, we have this equation. As a result, entropy is additive for independent random variables, which means this equation when x and y are independent. This lemma is crucial in understanding how joint entropy behaves, particularly emphasizing the additive nature of entropy for independent variables. Now here we discuss the chain rule for entropy. For a sequence of random variables x1 through to xn with the joint probability distribution, the chain rule for entropy states this equation. To understand this, let's consider the proof. First, we are starting with the joint probability distribution. This decomposition of the joint probability directly leads to the chain rule for entropy. We also have corollary 2 as follows. With equality holding if and only if the xi's are independent. This corollary highlights that the total entropy of a sequence independent random variables is simply the sum of their individual entropies. Now we introduce the concept of mutual information, a fundamental quantity in information theory. Mutual information measures the mutual dependence between two random variables x and y. It quantifies the amount of information obtained about one random variable through the other. The mutual information is defined as follows. This diagram illustrates this concept with x and y representing two random variables connected through a channel. This entropy hx represents the total uncertainty of x, while hy represents the total uncertainty of y. As information passes through the channel, mutual information captures the reduction in uncertainty about x given the knowledge of y. Continuing our discussion on mutual information, let's explore a typical example and further details. One typical example of mutual information is the communication channel with input x and output y. Here, hx represents the uncertainty of input x and hx given y represents the uncertainty of x after observing the output y. In fact, hx given y is equivalent to the information loss due to the noise in the channel. This means that any uncertainty remaining about x after observing y is due to the imperfections or noise present in the communication process. Mutual information therefore quantifies the average amount of information that y contains about x, or equivalently, the average amount of information that x contains about y. In this slide, we will explore mutual information with definition 6. For two random variables x and y, the mutual information between them is the reduction in the uncertainty of x due to the knowledge of y. Mathematically, this is represented as follows or vice versa. This can also be expressed as mutual information. Mutual information measures how much knowing one of these variables reduces the uncertainty about the other, reflecting the amount of shared information between x and y. Here, we further explore the properties of mutual information. Mutual information is defined as follows. We can see that the joint entropy can be written as this equation. And from this, it follows this equation. This demonstrates that mutual information is symmetric. This symmetry property highlights that the amount of information X provides about Y is the same as the amount of information Y provides about X. Now we present the formal definition of mutual information. Mutual information is defined as follows. It means that it can be also expressed in terms of the expected value. This definition captures how much knowing X reduces the uncertainty about Y and vice versa. Starting with the entropy definitions and conditional entropy and substituting these into the mutual information formula, we can write this following equation. And after that, we can rewrite the first term as follows. Now, we factor out the joint probability, and finally, we obtain this final equation. This completes the proof showing that mutual information can be expressed as the sum of the joint probability multiplied by the logarithm of the ratio of the joint probability to the product of the marginal probabilities. Here we summarize key properties of mutual information. The first property is that mutual information is symmetric. The second property is that mutual information can also be expressed as follows. The third property is that mutual information equals entropy if and only if X is a function of Y, and in this case we get this. The fourth property is that mutual information is always non-negative. This is because Hx given Y is less than or equal to Hx. The equality holds if and only if X and Y are independent. And the final property is that when X is considered with itself, the mutual information is equal to the entropy of X. Now we present a visual representation of the relationships between various entropy measures and mutual information. On the left, we have Hx means the entropy of X, which represents the total uncertainty about X. And on the right, we have Hy means the entropy of Y, representing the total uncertainty about Y. The yellow region within the left circle represents Hx given Y, which is the conditional entropy of X given Y. It quantifies the remaining uncertainty about X after knowing Y. Similarly, the blue region within the right circle represents the conditional entropy of Y given X, indicating the remaining uncertainty about Y after knowing X. The overlapping region in the middle, shown in orange, represents the mutual information. This is the amount of information shared between X and Y, reflecting how much knowing one variable reduces the uncertainty about the other. Finally, the entire area covered by both circles represents the joint entropy, which measures the total uncertainty about the pair X and Y. Here we introduce the concept of conditional mutual information. Conditional mutual information is defined as the common uncertainty between X and Y under the knowledge of Z. Mathematically, it is expressed as follows. This formula represents how much knowing Y reduces the uncertainty about X given that Z is already known. Now we introduce Lemma 7 regarding conditional mutual information. Lemma 7 is defined as follows. This lemma shows that the mutual information between X and the pair Y and Z can be decomposed into the sum of the mutual informations. Let's look at the proof for the first equality. Starting from the definition of conditional mutual information, we have this equation. And rewriting this equation using the chain rule, we get this equation. This can be simplified to this equation now. Thus, we have proved the first equality. In this slide, we present Theorem 8, which introduces the chain rule for mutual information. Theorem 8 is defined as follows. This theorem shows how the mutual information between a set of variables means x1 through to xn and another variable y can be decomposed into the sum of mutual information. To prove this, we start by expressing mutual information in terms of entropy and conditional entropy. We then applied the chain rules for entropy and conditional entropy to decompose these terms. By carefully breaking down the joint and conditional entropies, we arrive at desired sum of mutual information. Here we discuss the data processing inequality. The data processing inequality states that the mutual information between two variables cannot increase after processing. This applies to both deterministic and random processes. In simpler terms, by processing data, we can only lose mutual information, meaning the uncertainty can only increase. This principle ensures that any manipulation of the data does not add information about the original variables. The diagram illustrates this concept in the context of a communication system. We have a source U that is encoded into X, sent through a channel and then decoded into V. According to the data processing inequality, we have the equation as follows. This inequality shows that the mutual information between the source and the final output cannot exceed the mutual information between the variables at any immediate stage. Here we introduce the concept of a Markov chain. Definition 7 states that random variables x, y, and z are said to form a Markov chain in that order if the conditional distribution of z depends only on y and is conditionally independent of x. This means that once we know y, the variable z is independent of x. In other words, the future state z depends only on the present state y, not on the past state x. Mathematically, for the Markov chain, we have this equation. Given the Markov property, this simplifies to this equation as follows. This equation illustrates that the joint probability of x, y, and z can be decompressed into the product of the marginal probability of x, the conditional probability of y given x, and the conditional probability of z given y. Now we delve deeper into the properties of Markov chains with lemma 9. Lemma 9 states that x, y, and z form a Markov chain if and only if x and z are conditionally independent given y. To prove this, suppose we have a Markov chain and it follows this. This equation shows that the joint conditional distribution can be factored into the product of the individual conditional distributions, confirming the conditional independence of x and z given y. Additionally, corollary 3 states that if we have the Markov chain, then the reverse chain also holds. In this slide, we present Theorem 10, which relates to the data processing inequality in the context of a Markov chain. Theorem 10 states that for the Markov chain, the mutual information between x and z is less than or equal to the mutual information between x and y. This theorem implies that as information passes through y, the amount of information that x shares with z cannot exceed the information that x shares with y. To prove this, we use the chain rule for mutual information. Given the Markov property, we know that x and z are conditionally independent given y, so we have the equation as follows. This confirms that processing information through an immediate variable does not increase mutual information, aligning with the data processing inequality principle. Here we continue exploring the data processing inequality with a deeper look into the proof. From the definition of conditional mutual information, we have the equation as follows. And with Markov chain, we can get this equation. This follows directly from the property of the Markov chain, ensuring that given y, x, and z are conditionally independent. Now by substituting this result, we have this equation. Since we have this, it follows this equation. This conclusion aligns with the data processing inequality, affirming that processing through an intermediate variable cannot increase mutual information. Additionally, we have equality if when y provides no additional information about x beyond what z already provides. Now let's discuss the concept of entropy in the context of continuous sources. The Shannon entropy we have discussed so far is restricted to discrete sources, where the random variables take on distinct separate values. To address continuous random variables, we introduce the concept of differential entropy. Differential entropy extends the idea of entropy to continuous random variables, allowing us to measure the uncertainty of these variables. One key difference is that the entropy of a continuous random variable is theoretically infinite because the number of bits required to represent a real number is infinite. Therefore, we use differential entropy instead to handle this case. Differential entropy helps us quantify the uncertainty of continuous random variables in a meaningful way, similar to how Shannon entropy is used for discrete variables. Here we define the concept of differential entropy. Definition 9 states that the differential entropy of a continuous random variable x with a density function fx is defined as follows. Here, S represents the support set of random variable, which is the set of all possible values that x can take. In this slide, we illustrate the concept of differential entropy with an example. Consider a random variable uniformly distributed from 0 to a so that its density is from 0 to a and 0 elsewhere. The differential entropy for this random variable is given as follows. For a is less than 1, logarithm a is less than 0, and thus the differential entropy is negative. Finally, we conclude our discussion on differential entropy with an exercise. In the first part, let x be a discrete random variable and define y is equal to 2x. What is the relationship between hy and hx? In the second part, let this Gaussian distribution, which is continuous random variable, and find the hx in bits. And for the last part, if y is equal to 2x where Gaussian distribution, interpret the entropy hy in terms of hx and compare the results with part A. Please take some time to work through these problems. If you would like to know the answers and discuss your solutions, feel free to let me know in the comments. I hope you found this topic informative and useful. Thanks for your watching, and if you enjoyed the video, please like, share and subscribe. And don't forget to hit the bell icon for updates. Your supports help us to create more content. See you next time.